Hello everybody, my name is Thomas again, and today we are talking about the Proposition 4 of Leibniz's work on the quadrature of the circle, the hyperbola and the parabola. And Proposition 4 is to be understood rather as an emphasis on what has been laid out in the previous Proposition 2 and 3 already. And in the design of this proposition, we basically just focus on three elements, and this time we made up the series sort of variable by applying these little slider bars here, such that one can play around with the quantities of each element and see what happens to, first of all, the difference of the outer quantities and the sum of all differences in the whole series. So what applies to three elements would basically apply to a series of any number of elements. And what we're going to do is we're going to start now playing with the sliders. So what I do is I change the quantity of A to some value and it becomes clear that the quantitative difference between the first element A and the second element C, and the difference between those, which we call B, becomes like the same as element A, 303, because the second element C is 0. So this is still a natural order series because we have only a dissension in the series. So when you notice that when the first element A as an outer element is 303 and E as the second outer element is 0, then you see that the difference between those two is also 303. So in this particular case, the sum of all differences is equal to the difference between the outer quantities. So, and hence the difference between the outer quantities is, or in this case, not larger than the sum of all differences. So when we change that now, let's say we move C to some extent and then make it a different value. And you notice as long as the second element is smaller, in this case with a descending natural series, you see that the sum of differences is not going to change. Yeah, because the difference between the first and the second, A and C, is going to decrease when I put the slider upward, and the difference between the second and the third element is going to increase. So this compensates sort of each other, which has the effect that the sum of all differences stays at the very same number, right? And since I'm not changing any of the outer elements, the sum of all differences, or rather the difference between the outer elements, stays also at the same value. So what happens now if I make C larger than the first element? Then you see the series turns from being of natural order into a series of disturbed order. And in the series of disturbed order, we already found in proposition 2 and 3, the sum of all differences will always be larger than the difference of the outer quantities A and E. And you see, because I'm moving now basically away with this C slider here, away from the first element and also away from the third element quantity, this means that the quantitative difference between both of these elements, or between the C element and either one of these outer elements, is going to increase. So, and hence this is going to change the sum of all differences. So B is going to be getting larger and D as well. So the sum of differences therefore increases. But since I'm not moving the outer quantity A or E, the difference between the outer quantities stays the same. So however I move this C slider upward, the difference between this one, the sum of all the differences, and the difference between the outer quantities, they're gonna be the difference between them gonna be ever larger. So when I move the last element, being E, one of the outer elements, you see that as long as I am being smaller with the E quantity than with the A quantity, and I move toward the A quantity, of course the difference between the two outer quantities is going to be decreasing, and when I reach the same level as A, the difference of course is going to be 0, while the sum of all differences is still huge because I have the middle element, the C element, at a very high value. So, and you can actually see, as long as the middle element is between the quantities of the two outer elements, the sum of differences and the difference of the outer quantities is always going to be the same. But never ever is it going to be the case that the difference between those outer quantities is going to be larger. So you could put in any combination here. That's and should be meanwhile an established rule that these quantities between this one and this one never will get larger. So this value will never be larger than this value. And that's what he was just gonna show and emphasize once more, because it's gonna be, as I mentioned many times before, be quite important in the Proposition 7 when he actually is drawing out a proof for us in order to show that certain areas within the process of getting to the quadrature of the circle are equal. And yeah, we're gonna shed some light on this one once we get to Proposition 7. So this is all for now. So there was not much new information for those who were watching Proposition 2 and Proposition 3, but we steadily getting nearer where we supposed to be in order to tackle Proposition 6 and Proposition 7. So until then, stay tuned, and I hope you enjoyed it a little. Thank you very much, and bye bye.